right, guys, today we're going to extend what we did yesterday with some hypothesis testing with linear regression. We learned all about linear correlation and regression yesterday, and today we're going to do some hypothesis testing with it. Okay, so what the goal is to determine whether there is a significant linear correlation between the two variables. So our notation is the same as yesterday. N is how many pairs of sample data we have. R is the linear correlation coefficient for the sample. Rho is the linear coefficient for the population of paired data. That's the same as it was yesterday. All right, the requirements are also the same as they were yesterday. Just to review them real quick. The sample is from an SRS, simple random sample. Visual examination of a scatter plot shows that it's approximately a straight line pattern. The outliers must be removed if they're known to be errors, or the effects of outliers should be considered by calculating R with or without them included, just to double check. Hypothesis, test for correlation, hypothesis. Okay, so hypotheses. This is going to be our HO every single time. We're going to say rho equals 0. And if rho is 0, what that means is that there is no linear correlation. That's what that means. Okay, remember, the closer rho gets to 1 or to -1, the higher the correlation. If it's close to 0 or is 0, there's no correlation. So our alternate, or a ha, most of the time is going to be not equal to 0, which means there is a linear correlation because it's not 0. Our test stat's going to be R, and we're going to use technology obviously to find our p-values and critical values and things as to the table, and we'll get to that soon. All right, hypothesis test for correlation. If R, when you calculate your R, is greater than the critical value, we're going to reject the null. If R is less than the critical value, we're going to fail to reject the null. And remember, the null was that rho is 0, or that there is no linear relationship. So if we reject the null, we're saying that there is sufficient evidence to support the claim of linear. If we say we're failing to reject the null, that means there's not sufficient evidence to support the claim of a linear correlation. All right, let's do the same as now. If you didn't watch yesterday's video, this next part probably won't make any sense. I'm stealing the example we did yesterday where we did height and shoe size, and our R, this is the same R we got yesterday, it was 0.591. And so if I'm going to conduct a hypothesis test to see if there's linear correlation, I'm using 0.05 for my sig level. All right, so here's my claim. Ho is always, rho is equal to 0, means there is no linear. And my claim is that, the claim is this one, that there is a linear correlation. So there's our test stat, 0.591, and I found the critical values, which are plus or minus 878, and N was 5, there's my sig level. So because my R does not fall past my critical value, it does not fall in the rejection zone. So I would fail to reject the null, and I would conclude there's not sufficient evidence to support the claim of a linear correlation because I'm not rejecting that one. All right, the p-value method, which to be honest, that's one we're going to use the most for our hypothesis test. Our test stat is right here. That's the formula. Our computer's going to do that for us most of the time. P-values can also be found using software, which is what we're going to use the most. But so the P and T kind of go together. So here we go. All right, continuing the same problem. I went ahead and showed you here all the numbers and calculating your T-stat because you knew what all these letters stood for anyway. That was my T-stat, and our P-value, when we punched it in, gave me 0.2937 for a p-value, which is obviously higher than 0.05 or 0.01. I think this problem was using 0.05. So because the p-value is that, which is greater than 0.05, because it's so high, we're going to fail to reject the null. And the conclusion then is that there is not sufficient evidence to support the claim of a linear correlation between shoe size and height. Because the p-value is too high. And don't forget what your HO and HA are going to be all the time. Okay, there's also such thing as a one-tailed test when you're testing linear correlation, which is kind of what you're used to anyway. Same as you would think. If they claim that there's a negative correlation, instead of just saying that the rho is not equal to 0, we're going to say rho is less than 0 because we're saying there's a negative correlation. If the claim is that there's a positive correlation, we're going to say that rho is greater than 0 because that's where the positive numbers are. So for this sentence down here is huge. For these one-tailed tests, the p-value method can be used just as it was in earlier chapters, or all the times we've used our p-value, you can do it the same way here as we've done the whole rest of the semester or whatever. So hope that wasn't bad. As usual, work on it tomorrow, do some hypothesis testing with linear correlation. You'll love it. See you in class tomorrow.